So what we're going to do today in 12.5 is talk about exponential growth and decay models. So this is our general form right here. Everything that we do in 12.5 is going to have this format right here. So first thing I want to talk about is what do all the different parts of this mean? And I have them for you in this table here. A is our population after some time. So for us, A is all that we're going to be solving for. If you take 163, you could solve for other parts of this, but for us, we're always going to be finding what the population is after some amount of time. This A with the little 0 next to it is pronounced A naught. That's our population at the start. So think of 0, the little naught there, as like times 0. So the A stands for population at times 0. So A naught is our population at the start. So if you ever need to know starting population, just look at this number right here in your equation. That's where you started. E is a number. So we talked about that some back in 12.2. E is kind of like pi. It's an irrational number, 2.71, non. So that's where you need your calculators. You're going to need your calculators because these have that E value in them, not something that you could do by hand. Then on our E, there's an exponent, and that's got two different parts to it. The first is K. That's our constant of growth or decay. So K is a constant. So K is a number that you'll be given in these problems. The only other thing we really have to figure out is T. And T is our time. We want to know how long are we from the start time. So if we're starting something in 2001, I might say, what's the population then in 2013? So we're going to have to see what the time that has elapsed from our start time is. Yeah?
I thought the formula was something like R over N or something like that. Like N times T.
I mean, there are different formulas depend on. This is for the particular types of population growths and decays that we're working with, an exponential with E. Sometimes, too, you get ones that aren't maybe as exact, but E is one of these numbers that you see all the time in these sorts of problems. Yes, there are other types of equations that represent this. This is the particular one we're working with for this section. So when we want to evaluate our exponential growth or decay, we're going to fill in all the numbers that we need and figure out what the time is, the time from start to where you're asked your question. And then use your calculator to evaluate that number. So we're always just looking for the population after some time. You're not going to have to solve it for other times. So the exponential, it should say model, describes the population of Iraq, A, in millions years, T years after 2006. So A is our population in millions, and T, our time, is measured in years. And we're starting in 2006. So this is our start time, 2006. So everything else we do after that is going to be based on the fact that we started this measurement in 2006. So the first question is, what is the population of Iraq in 2006? Now this is a problem where you actually don't need to do any work if you know what the different numbers in your equation stand for. Or if you want work, there's a way to do work for it. So based on what we said, all of the different parts of this equation are, which number down here represents the starting population? 26.8. So whatever the number is in front of E, that's our A naught. That's the original amount or starting population. So if you're asked the population in 2006, how many years is that from my start date of 2006? 0. We haven't gone anywhere. We're at our start time. So since we haven't changed years yet, the number in your equation here is always the initial population. Yes?
What's the E stand for?
E is a number. So if you go back, we did this right here. So E is an irrational number. It comes from this right here, which is approximately 2.71. Okay. So E is just a number. It's not a variable. So if you're ever asked for the population at whatever your start time is, it's in your equation. It's the number in front of the E. The other way, if you wanted to do work for this, which Don't do work if you don't have to. But the other thing you could do is say, I'm looking for the population. And take my equation. Everything here is set up for me except the time that's elapsed is 0 years. So I'm still in 2006. And what's going to happen to this exponent if I multiply 0.027 by 0? 0. So 26.8 times e to the 0 power. But what's anything to the 0 power? So it's just 26.8 times 1, which that's, you see how that number is then our starting population. Because if you're at time 0, this is always going to be e to the 0, which is multiplying by 1. But you don't even have to do that work. It's the number in front of the e is always your starting population. It's what that number represents. So 26.8 million people. Now the next question is, what is the projected population in 2025 round the projected population to 1 decimal place? So the only number that we need to figure out is what's going in for t. We need to know how much time has elapsed between our start time and the time we're projecting. So our projected time is our 2025. Just subtract from that your start year. So we're looking 19 years down the road. So we're going to take our equation for our population growth, 26.8 e to the 0.027. I'm actually going to do times 19. Because when you put this in your calculators, and that's what we're going to talk about next, all of your calculators that hold the display, when you use the E button, will automatically put it raised to the power and then parentheses. So you want parentheses around the exponent. So let's talk about the different calculators. Let's start with the graphing calculator, folks. You can enter this all at once. You don't need to do this piece by piece. So for graphing calculators, type in your 26.8 and then hit second and the ln button, that's our natural log. If you hit second ln, you should see it looks like this, 26.8 e up parenthesis. Then type in 0.027 times 19 and close the parentheses. And that'll give you your answer. For people who have one of these scientific calculators that holds numbers, and Daniel, yours should be the same as well, or similar. So type in your 26.8 and second natural log again gives you the e. So second and then just 2 buttons down is the natural log. And then it will look just like this. Raised to the power and it will open a parenthesis. Type in 0.027 times 19 and close the parenthesis. For people who have calculators that don't hold the displays, it's a little bit more work because you have to do this in 3 pieces. So if you have one that looks like this, what you have to do first is multiply the exponents. So you're going to do the 0.027 times 19 and then hit equals. Now hit second and your natural log button is over to the right of that. Second and then natural log. And that's doing, now you've done, you're working backwards essentially. Now you've got an e to that power. And now hit times the number out front. So with one of these calculators, you're really working right to left. You multiply, you do the e, and then you multiply by 26.8. Were you able to figure out yours? So what do we get for a population? Rounded to 1 decimal place, 44.8 million people. Was everybody able to get the 44.8? Anybody else unable to get the 44.8 million? What do you have for a calculator? You guys have the widest substitute in your numbers, put it in your calculator, get your answer. So the next one says complete the table, round the projected population to 1 decimal place. We've got 2 countries. We're starting in 2007 for both of them. And for both of them, we want to find their projected population in 2030. And then you're given their growth rate K. So the first thing we're going to need for both of these is fill in a little bit more in those equations. So let's start with Madagascar. Now in general, I'm going to copy this over for the front. We're looking at A naught, E to the K, T. So for Madagascar, what number am I going to put in for A naught? 19.4. That's always your starting population. So we're going to start in 2007 since that's the population they've told us. So we're going to do 19.4 E. And then they tell us what our constant is, what K is. That's the last bit of information in the table. So in place of K, we have 0.0285, and we're multiplying that by T. So if you want to set it up to look like the other problem, we've got our starting population goes in place of A naught, and our constant goes in place of K. And now, how many years down the road do we want to project the population? If we started in 2007, and we're looking now at 2030. 23 years. So if you take where you're going and where you started, we have a difference of 23 years. So all we have to do is go into our equation and substitute in place of T 23 years. And for most of you, when you use your calculator, make sure you put parentheses around what you're multiplying in the exponent. So take a moment, make sure that we can all get that answer, because most of 12.5 is, can you accurately put it into your calculator? You have to know a little bit about what the different numbers represent, but after you get your numbers in, it's just substituting, plugging them into your calculator. Did you do the E anywhere?
What?
Did you do the E part anywhere?
No.
No. So,
Well,
okay, so
I
multiply.
don't really remember the process.
Right.
I know
Multiply.
Okay.
And then you gotta get second ln to get the E part.
Oh, okay. That does it just right. Okay.
And then times.
Okay.
Is it 0.078?
0.02.
285?
Yeah, it's this number right here. So what is our projected population of Madagascar in 2030? Again, rounded to 1 decimal place. 37.4? 37.4? Anybody not get 37.4 million? You won't see the million on your calculator. Now, I know about Bulgaria, and Bulgaria is changing population. Notice up to this point, all of our K's have been positive. When K is positive, you have a growth. The population got bigger. It started at 19.4 and went up to 37.4 million people. But for Bulgaria, our constant here is negative. So what's happening is the population is actually going down. So So we're going to see that in 2030 we have less people than we started with in 2007 because our constant is negative. So for Bulgaria, if we fill in our numbers, we're looking at A equals 7.3 e to the negative 0.0082 t. And then, because we're filling in the same table with the same start time and the same end time, what's t? 23 again. And then it's a matter of, oops, I put in 0.0083 there for some reason. It goes maybe saying 23. 0082. So then using your calculator, we want to find out, rounded to 1 decimal place, Bulgaria's population in 2030. What do you got? 6.0? 6.0 because it's, but it's 6.04. So the 4 tells you to keep it at 0. So it would be, so you get 6.04 and on. When you look to the right of the 0, the 4 doesn't tell you that you can move that up. So it is just 6, or you could say 6.0. You could write just 6, because when you round that, we don't have enough to bump that 0 up to a 1. So they started at 7.3 million. In 23 years, they're projected to go down to 6, because that K was negative. Questions? I think in all the problems, I'm trying to think of like where I've seen them. You'll have the formula. It just happens to be on this particular part of your homework. They give you the table, so they didn't. But it'll be something like C, where it's part of the problem. So for C, an artifact originally had 15 grams of carbon-14 present. The decay model, A equals 15e to the negative 0.0001 t, describes the amount of carbon present after t years. How many grams of carbon-14 will be present in 7,125 years? So there's a lot of information in that problem, but just a couple things that we actually care about. So the things we care about, you should always care about if they give you something to work with, an equation to work with. So it tells you right there how we're going to represent this decay. And we know it's a decay because the constant here is negative. That tells us it's a decay. Robert?
How many zeros are under that one?
The ones that, there's 3 zeros that matter. 0.0001. You really don't need to leave this 0 on there. Another just note in the words, because it describes a lot of stuff. Notice how it says it originally had 15 grams of carbon. There's the 15. That's our original amount. That number in front is always the original amount. So we want to see how much is going to be left after 7,125 years. You'd think it might not be a lot, but this doesn't have a very fast decay rate. Oops, let me do time.
That is 7,000 years.
We'd expect it might almost be gone then, right? 7,000 years down the road. So see what you get when you substitute that in. Round this one. I think in your homework they might round it to whole numbers just based on that answer right there. You can still round it to 1 decimal place. That'd be safe. On your test, I'll tell you how many decimal places to round to. Fingers crossed on your final, they tell you how many decimal places to round to. 7.4. So that's half. Little less than half. So what are we working with? Grams. In 7,000 years, you're only losing half of that carbon-14. A little bit more than half. So is everyone able to get those numbers? All right, so for our first classwork, we're going to have 2 classworks today. They're both 3 problems. I'm going to have you do 2 problems like this. Let's go back to 12.4. and finish up solving logarithmic equations, which we've already done one version of this. We did this on Monday. Your drill from last class had problems like these, except last class you had the problems that said evaluate. Evaluate the expression. We put equal to x, rewrote it, and solved it. The difference here is that you have a full logarithmic equation, and we need to solve it. And there's three different places that I can put x. I can put x as the base. I can put x as the number you're taking the log of. Or I could put x on the right. This is the type that we did all in 10.2. We did everything looking like that. But now we're just going to move the x around sometimes. So to solve our logarithmic equations, first thing you want to do is rewrite it in exponential form. And then once it's in exponential form, there's going to be a few different things you might do depending on where the x is. So we're going to solve it or evaluate it. And then it says check to make sure your solution's in the domain. We're going to have solutions that are all in the domain. That's just a step because of the directions in your homework. So the directions, solve each logarithmic equation. Be sure to reject any value of x that is not in the domain of the original logarithmic expression. We're not going to worry about that part. All of our values will be in the domain. Give the exact answer. Then, when necessary, use a calculator to obtain the correct answer to 2 decimal places. So if you have a fraction, that's okay. But if you have e to some power, which is what we're going to be looking at, I need exact answer and approximate answer. So for the first equation, we have a log base 2 of x equals 4. To solve these logarithmic equations, first thing to do is to write them in exponential form. So if I'm going to put this in exponential form, what is my base? 2. The base is your base in both forms. And then what's the exponent? 4, other side. So this is back to what we were doing on Monday. And that equals x. So now this is the part where the solving can be a little different depending on where the x was in your equation. So I have 2 to the 4th equals x. But we want to evaluate all numbers to powers. That rule goes back to 10.2. So what's 2 to the 4th power? Once we know 2 to the 4th, we've got x. 16. So there wasn't actually any solving. All we had to do was evaluate 2 to the 4th power because x was already by itself. Now for the second one, we don't have the log. We have ln, which stands for natural log. The natural log of what number equals 3? Does anyone remember another way we could write natural log? Not just e. E is a number. It's not the same as a natural log. ln e is 1. You're getting close. But ln, there's another way I can write ln. We gotta go back. And that's just a regular log. Getting closer. We gotta put all these ideas together. It's a log base e. So if you look back at 12.2, wherever you have a natural log, we could replace it with log base e, and that's the same e that we were just dealing with in all of our growth and decay models. It's just a number, 2.71, on. So whenever you see ln in one of these problems, we're going to replace it with a log base e, because we really need to see that base in order to go between our two forms. So the natural log is just a short way of writing a log base e, which if you go on to another, like a 163, you're going to see natural logs. They're very useful all over the place. But for our purposes, we're going to replace it with log base e. And then I'm switching forms. So I had to take an extra step to expand that natural log to a log base e, but now I'm going to write it as an exponential, now that I have a base. So the base of my log is the base of my exponential. Go to the other side, and that's equal to x. So our exact answer, which you do need to have, it's in the directions, the exact answer is e to the 3rd power. Just like 2 to the 4th power, we can evaluate to a number. E to the 3rd power is a number. But it's an irrational number, so we're going to have to round it. So the exact answer is e to the 3rd. But now we also want to know, so it's exactly e to the third. We want to know what it is approximately, rounded to 2 decimal places. What was that? It's 20.09. So using your calculator, using that E button, that sounds right. Using that E button, like you did in the population problems, find e to the third power.
You said rounded to 2 decimal places?
Yes.
20.09?
Yes. So is everyone able to get the 20.09?
No, no freaking clue.
For you, you've got to work right to left. Enter 3. And then second, or
That's it?
yeah. Yeah, it doesn't have a whole lot of multiplying like the other problems did. So you need both of those, though, because it wants exact and approximate. E to the third's exact, approximate 20.09. Questions? Now C is actually exactly like what we did on Monday because the X is on the right. All of the problems we did on Monday had the X on the right when we were evaluating. So the first thing we need to do is to change the format to exponential. I'm going to have 7 raised to the X power equals 1 over 7. So 7 to what power is going to get me just to the fraction 1 over 7? Negative 1. So the fraction means the exponent's negative. 7 to what power gives me 7? 7 to the first. So x here has to equal just negative 1. Just to get me to that 1 over. For D, our x is now our base. So we have x to the third equals 27. So what number raised to the third power gives me 27? 3. So x has to equal 3. Now there is a way that you can solve that if you wanted. We didn't actually do this, but we could extend on an idea that we have. How might I get rid of a cube? What's the opposite of cubing? Cube root. So that we did the opposite of squaring is a square root. Here you could do the opposite of cubing is a cube root. You don't need a plus or minus with a cube root. So that'd be another way that you could get to 3. But the problems I give you, you should be able to look at them and say what to the power gives me. All right, for E, we have a log base 64 of what number? Equals 1/3. So when I rewrite this, I have 64 to the 1/3 power equals x. So this is going to be another evaluate, 64 to the 1/3 power. Now, you could put that in your calculator, but we know something else about the 1/3 power from 10.2 and from 12.2. What is the 1/3 power the same as? Cube root. 1/3 power, if you think back to 10.2, we did one of these. Index. 1/3 power is the same as the cube root of 64. Again, you could also put that in your calculator because nowhere in the directions does it say anything about needing to use radical notation. We're looking at the cube root of 64, which is 4. And then finally for F, just a little bit more going on, but it's the same process. Take our base, which is 2. I'm going to raise it to the power 5, and that equals 4x plus 1. Where do you think we're going to have to start for the solving here? 2 to the 5th. We want to replace 2 to the 5th. So 2 times 2 times 2 times 2 times 2. 2 to the 5th power. We're going to start by replacing that as 32. And then from there we can solve. So I'm going to subtract 1 from both sides. So I have 31 equals 4x. and divide by 4. So x equals 31 over 4. Now, if it's a nice fraction like that, I'm okay with you leaving it. Someone in the other class is like, well, they did ask for decimal answers. So you could go ahead and divide that. It is exactly 7.75. For a fraction, I don't mind if you just leave the fraction. But for the E ones, you have to change. You have to give the approximate. Questions?